Hello, everyone. My name is Jasmine Aloor, a PhD student at MIT AeroAstro. I will be presenting our work titled Decentralized Autonomous Traffic Management Through Corridor Networks. This work was done jointly with Aadarsh and advised by Professor Hamsa Balakrishnan at MIT. This is a video taken in Manhattan in New York City on April 27, 2026. That is a Joby S4, an autonomous capable air taxi on a demonstration flight. And operations like this are about to scale across the US in a fundamentally new way. This is one example of Advanced Air Mobility, or AAM, a new class of aircraft in operations designed for short-range urban and regional flight. As of 3 months ago, the FAA's eVTOL Integration Pilot Program selected 8 projects across 26 states, with operations starting this summer. The US AAM market is projected to be over $90 billion by 2035. Further, the scale AAM is being designed for is different from today's regional aviation. We're talking about sustained operations at densities that today's air traffic system was not built around. And lastly, even though Joby's operation we see here is piloted today, the design trajectory is towards increasing autonomy. Wisk is designing for autonomous operations from day one. Beta and Archer have optionally piloted an autonomous variants in their EIPP project. And the next slide describes how AAM differs from what today's system was designed around. Today's air traffic system was designed for a particular operating regime, and it works extremely well within that regime. Controlled airspaces have centralized human-in-the-loop coordination, with controllers managing each sector. But the AAM operation regime is different in the following ways. And these are what motivate the research community's interest in new coordination architectures. First, density. AAM concepts are designed for sustained operations at much higher density per metropolitan area. AAM also spans the full autonomy spectrum, with the trajectory clearly towards greater autonomy. Initially, we will see a mix of piloted and remote piloted and autonomous, but as operations mature, it will lean heavily towards autonomous operations. Third, with fleet heterogeneity, today, aircraft within a class are relatively homogeneous in performance, but AAM brings a heterogeneous fleet mix and ranges. Fourth, on demand. Today's commercial aviation plans routes and schedules weeks to months in advance. AAM is designed for on-demand services. On separation, today it is controller provided with TCAS providing advisories for imminent collision. But AAM will require onboard tactical separation, such as sense and avoid or other sophisticated methods. So as autonomy and AAM operational density increases, the natural question is, what coordination architecture supports it? And that question does not have a single answer. There could be a spectrum. On the left, we have fully centralized coordination, where a single service provider within an airspace operating with system-wide information, supported by centralized scheduling and traffic flow management, with full information visibility can enable efficient coordination. In the middle, we have federated coordination, where responsibilities are distributed across multiple providers, operating under common rules through shared information structures. The FAA's UAM ConOps and the CESAR's USpace both adopt federated architecture. Today's operations, in fact, lie between the centralized and federated architectures, where multiple air navigation service providers coordinate across borders, but most coordination authority still sits at the centralized end. And on the right, we have fully decentralized coordination, where each aircraft makes decisions based on local information on board. There are rule-based approaches and learning-based approaches. Our work explores the decentralized end of this spectrum. We want to understand, can aircraft coordinate using only locally observed states of their neighbors? And what does performance even look like? Understanding what's achievable at that end of the spectrum tells us something about where the floor is, and that's useful regardless of whether real systems end up there or somewhere in between. There's a second design dimension that's just as important. Coordination decisions in air traffic management happen across a range of timescales. The previous slide asks who decides. This slide asks when. At the top, we have strategic operations on the order of minutes to hours. This is where flight planning, ground delay programs, slot allocation, and demand capacity balancing live. Strategic deconfliction also sits here. At the bottom, we have tactical operations on the order of sub-seconds to seconds. This is where TCAS and ACAS live and where recent research on runtime safety filter operates. These are mechanisms operating at the timescale of an imminent loss of separation. The work I'm presenting today is positioned between these two. We're not scheduling departures upstream, and we're not resolving last-second conflicts. We're continually guiding the aircraft, providing turn rate and acceleration commands derived from each aircraft's local observation that shapes how aircraft traverse over a timescale of seconds to minutes. We call this the flow shaping layer. Decentralized learned guidance can shape sustained traffic flows effectively, and at the end of the talk, I'll show you some work that we are doing to add a tactical safety layer underneath this kind of flow shaping policy. So I just described the design space at a general level, who decides and on what time scale. The specific operational context this work studies is corridor-based operations, which both the US and European regulators have adopted as a structural element for AAM. Corridors are defined volumes of airspace with structured, predictable flow paths. We've been organizing high-density traffic with structured routes for decades through oceanic tracks and standard arrival and departure routes. Corridors apply the same principle to AAM. What corridors do is reduce coordination complexity. By constraining aircraft motion to designated routes, the geometric problem any coordination scheme has to solve becomes much simpler than free flight. But corridors don't eliminate coordination. Inside a corridor network, all aircraft still need to maintain separation and do all of this efficiently at AM densities. So the question we ask is, within corridor networks, can autonomous aircraft coordinate in a decentralized manner using only locally observed information and still produce efficient corridor-conformant traffic flows at scale? The rest of the talk addresses this question. Before describing the approach, I want to outline the key operational and technological assumptions in this study. First is airspace structure. We assume corridors exist as a known static structural element. We're not designing the corridor networks, we're studying coordination within them. We also model all aircraft with planar fixed-wing kinematics. Second, sensing and information sharing. Each aircraft observes its own state plus the relative states of nearby aircraft within a sensing neighborhood. The current or next corridor's relative position and orientation are available to aircraft. Notice that the aircraft's view of the airspace is limited to the current corridor. Third is communication. The observation model requires synchronous and accurate relative state observations. In practice, this cooperative broadcast could be through ADS-B or onboard sensing at an update rate compatible with the control loop. We don't model communication delays, dropouts, or uncertainty in the study. Characterizing how the policy degrades under those conditions is a prerequisite for deployment and is part of future work. Fourth, operating conditions. We train and evaluate under nominal conditions with no wind or disturbances. So with these assumptions in mind, here is the methodology. Our approach for decentralized coordination uses multi-agent reinforcement learning, or MARL, as a tool to study what coordination is achievable under a strongly decentralized operation. The methodology has 2 stages. In training, the system learns a policy by running many simulated episodes in a simple environment with 1 corridor, 5 aircraft, with all of them having the same speed range. The geometry and starting positions are randomized every episode, and the 3 thumbnails on the left show some sample initial conditions. Every quantity in the observation, the position, speed, heading, is expressed in the aircraft's own heading frame. This means that a policy trained in a single corridor at a fixed orientation should, in principle, work identically in a corridor at any other orientation. This is the property that lets us train in 1 corridor and then deploy in networks of many corridors at varied orientations without retraining. What the aircraft does with those observations is command a turn rate and an acceleration within fixed wing performance limits, and that's the action space. The policy converts observations into those 2 control commands, and training itself takes a few hours of GPU compute. The output is 1 policy. Every aircraft in evaluation uses the same one, and there is no per aircraft customization. Evaluation uses the same trained policy with no additional retraining. The training environment was a single corridor with 5 aircraft and a fixed maximum length. The evaluation environment scales all of those up to varied corridor networks, up to 40 simultaneous aircraft, longer corridors, and a network the policy has never seen. One thing worth noting about how this generalization is possible is that the policy never sees the global network structure. At any moment, each aircraft has access to its current corridor geometry or the next corridor's entry point, orientation, and exit. Operationally, this means the information required is modest, and a vertiport or service provider only needs to communicate local corridor information to aircraft entering its airspace. So in this work, we measure 4 things in each scenario. Corridor boundary conformance, which is what fraction of the time aircraft stay within the corridor walls while traversing. Task completion rate, which is what fraction of aircraft reach their assigned exits before the episode ends. Third is average speed across each aircraft's traversal. And the fourth is the need for tactical intervention, which is the number of times an aircraft would require an external safety mechanism to maintain minimum separation. This one is the closest analog to a TCAS-style resolution advisory. The evaluation varies 3 things together: topology, density, and fleet composition. The next set of slides walk through each. The first 3 evaluation scenarios are progressively more complex topologies. The same policy that was trained on a single corridor gets deployed on each of these networks without any retraining. Across each topology, we evaluate 4 densities with 10, 20, 30, and 40 simultaneous aircraft. Here's what those policy executions look like in practice. First is the merge, where 2 upstream flows converge into one, with 3 total corridors. And the coordination demand here is sequencing through the merge point. The second is a split merge, where aircraft diverge into parallel lanes and reconverge downstream, with 6 total corridors. The third is a double merge, where we have 2 sequential merge points with 5 total corridors, with the interaction density compounding because aircraft that just merged are immediately approaching a second merge with new aircraft entrants. Across all the 3 topologies, we have high corridor conformance at 98% or above, and completion rates stay high. The tactical intervention rates stay within 6%. 3 to 6 corridors is, of course, relatively simple. The real question is what happens when you scale up. Here's the network we built to test the policy at scale. We have 18 corridors in total, 3 entry points, 2 exit points, and 8 possible routes through the network. We designed this by combining every interaction type we tested in the simple topologies with merges, splits, and sequential chains into a single network at high density. The video on the right shows what happens with 10 aircraft simultaneously traversing this network. I want to re-emphasize one critical thing. The policy on the aircraft in this network is the same policy trained on a single corridor, and the aircraft themselves have never seen this map. Each aircraft only knows its current corridor's geometry and the next corridor's location and orientation and where to enter. From the aircraft's perspective, traversing an 18-corridor network feels identical to traversing a single corridor with the next corridor handoff happening one corridor at a time. So what we are testing here is whether a local policy can produce coherent global flows in a network that it has no map of. Here's what the traffic pattern of 10 aircraft flying through the 18-corridor network simultaneously looks like. Each line is an aircraft trajectory colored by instantaneous speed, with blue being fast, around 175 knots, and yellow being slow. What we immediately notice is that aircraft maintain high cruise speeds inside the corridor, with the blue color dominating. The heat map on the right confirms this. Average speeds across the corridor segments stay high throughout the network, with only a modest speed reduction at the merge points. The speed reductions happen at 2 places, the merge junctions and just before the final corridor, which tends to be the most congested. As aircraft approach a merge point, the interaction density spikes, and the policy responds by slowing aircraft down to create spacing before they reach the merge. Now let us look at a throughput plot which measures the instantaneous outflow rate of the aircraft through the corridor network. This is a throughput plot for the most demanding scenario of 40 aircraft simultaneously in the 18-corridor network. The solid black line is what our policy actually achieves. The dashed blue is an upper bound computed assuming every aircraft flies at maximum unimpeded speed along a conflict-free trajectory. We reach a maximum of 14 aircraft per minute against this upper bound of 15 aircraft per minute. With centralized coordination and more information, we could get a throughput that lies between these two upper bounds. Across all traffic levels, we still get high conformance and completion rates, and the tactical intervention stays below 5%. Let's look at a heterogeneous fleet. Real AAM operations will not have identical aircraft. Different platforms will have different cruise speeds, so we tested how the policy behaves with mixed performance fleets. We took the same 18-corridor network and assigned 3 of the 10 aircraft a maximum speed of 140 knots, roughly 20% slower than the other 7, which retained their 175-knot maximum. We have the same trained policy, no retraining, no change to the reward structure. We just run it. Watch what happens in the simulation at the inter-corridor gaps. The faster aircraft slow down behind the slower ones inside the corridors. They cannot safely pass without leaving the corridor. But the moment they reach an open gap between the corridors, they extend their path and overtake. We did not program this. There is no overtaking reward. The behavior emerged from 2 things the policy learned: stay in the lane and make forward progress. When these 2 objectives interact with a slower aircraft blocking the path, overtaking in the gaps become the natural solution. Let's look at the trajectories. The black squares mark where the slower aircraft start. Look at what happens between the corridor. The faster aircraft extend its trajectory slightly outside the immediate corridor lane and overtakes the slower one. As soon as the next corridor's entry approaches, it re-enters the lane and resumes corridor conformance flight. The throughput plot shows the peak throughput of the policy dropping by a little as expected, and slower aircraft act as moving constraints in the high-density segments, and I'll show the comparison with the homogeneous case in the next slide. This is the comparison. On the left, the speed heat map is from the homogeneous case, where every aircraft was at 175 knots maximum speed. On the right, we have the same heat map, but with 3 of the 10 aircraft slowed to a max speed of 140 knots. The takeaway from this side-by-side comparison shows us the cost is spatially concentrated. If we look at where the heat map turns lighter on the heterogeneous slides, the differences cluster around the corridor segments that have the slower aircraft traversing. So we can conclude that the heterogeneity reduces the throughput in a spatially localized way. To summarize, we presented a multi-agent reinforcement learning-based approach to decentralized traffic flow management for autonomous AAM operations in corridor networks. A single policy trained on one corridor with 5 aircraft deploys without retraining across progressively complex networks, up to 18 corridors and 40 aircraft, across heterogeneous fleets with mixed performance envelopes. This work provides us a reference point. It tells us what is achievable when coordination is pushed to a strongly decentralized end of the design space, with aircraft acting only on locally observed states. The real AM system's performance will lie somewhere between this extreme and that of centralized coordination. And knowing what's at each end of the design space and what it costs is what makes choosing intelligently between them possible. And that's the contribution this work tries to make. This work characterizes what's achievable at one end of the design space. But there's room to do better, and 3 threads of ongoing work addresses that. First is a tactical safety layer. The work I've shown is in the regime of air traffic management with flow shaping above the level of imminent conflict resolution. The natural extension is to push the framework toward air traffic control, adding a runtime safety filter that guarantees collision avoidance. Second, integrating hard safety constraints into the learning framework itself. Our prior work on layered safe MARL for merged scenarios in free flight settings without corridors showed how policies can learn to slow down earlier and make proactive decisions to manage congestion when paired with a safety filter during training. And third, dynamic corridor networks. The corridors in this work are static. The network topology doesn't change during execution. But real airspace will have corridors opening and closing dynamically based on weather, demand, and traffic conditions. We haven't tested what our policy does when the topology changes at runtime. So each of these threads addresses a specific limitation of the work I showed. Together, they trace the path from characterization of the decentralized end of the design space towards systems that could actually deploy. Before I end, I'd like to acknowledge my co-authors Aadarsh and Professor Hamsa Balakrishnan, and our funding from NASA and the Air Force AI Accelerator. Code and additional materials are at the website shown. Thank you.